So I have a combinational logic circuit with only AND gates, OR gates, and NOT gates. What I want to do is I want to represent the same circuit using only NAND gates, or the entire circuit using only NOR gates. When doing this change of representation, I'm not considering the timing of the circuit, only the truth tables of the inputs and outputs. I'm going to be taking advantage of these four equations. So the big thing here is I'm going to abuse the notation, and I'm going to treat all the bubbles as inverters and all the inverters as bubbles. So when I say bubble, I just mean the bubble at the end of this NAND gate here. I'm not considering it as a NAND gate, I'm considering it as an AND gate with a bubble at the end, meaning the output of the AND gate is inverted. And so I'm only considering the AND gates and the OR gates. So if you do that, then when you apply De Morgan's theorem to this AND gate, it changes to an OR gate with all the inputs and outputs inverted, represented by bubbles here. And when you do the same to an OR gate, it changes into an AND gate with all the inputs and outputs inverted, which I represent using bubbles. And so this applies to like NAND gates as well. I'm treating this NAND gate as an AND gate with an inverter on the output, so I'm representing as a bubble, so that changes into an OR gate with the both two inputs bubbled. So I'm going to represent this example circuit using only NAND gates. And so I'm going to transform this OR gate into an AND gate using De Morgan's theorem and inverting all the inputs and outputs represented by bubbles. And so now, since I'm treating all the bubbles as inverters, I'm going to move all the bubbles going into the input for this NAND gate. I'm going to move all the bubbles to the outputs of these two AND gates. So by doing this, I am acquiring all NAND gates. So when I want to represent my circuit using only NAND gates, I'm going to transform all the OR gates into AND gates using De Morgan's theorem, and then moving all the bubbles around so that I acquire as many NAND gates as possible. And then I'm going to do the exact opposite when I want to represent the whole circuit using only NOR gates. I transform all the AND gates into OR gates using De Morgan's theorem, and then I move all the bubbles around to acquire as many NOR gates as possible. Then to take care of stray bubbles, I'm utilizing that we're using the bubble to represent an inverter or a NOT gate, and a NOT gate has the same truth table as a NAND gate with both the inputs coming from the same wire, or a NOR gate with both the inputs coming from the same wire. So let's pretend we did all of our transformations and we ended up in a circuit that looks like this. So we have this extra bubble here, and we want to remove it. We want to put this circuit into a form that is not ambiguous in the way it should be represented. So what we could do is since this one wire is bubbled twice, that means it's inverted twice, so we could annihilate these two bubbles. But the problem then is this gate becomes an AND gate instead of a NAND gate, and we want to have all NAND gates. So since we know we need to keep this NAND gate here and then just invert this wire, all we have to do to implement this inverter is change the bubble into a NAND gate with both inputs coming from the same wire, which looks like this. So now we ended up with our circuit with only NAND gates, and we took care of that stray bubble by changing it into a NAND gate with both inputs coming from the same wire, meaning it acts as an inverter.